So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be going over LLVM compiler infrastructure. Now LLVM is an absolutely fascinating piece of software and the idea is this. How can we make it easier? How can we make it faster? How can we introduce more reuse of code in the compiler development world? Now, first of all, let's take a bit of a step back and let's start off by talking about compilers. Now, of course, as developers, what you interact with on a day-to-day basis would be compilers. Whatever you write C or C++ or Swift or Julia or Rust code, you are interacting with a compiler. When you write, say, Python code or Ruby code, you're interacting with what's known as an interpreter. We'll talk about those later and why they're special, but for today, let's talk a bit more about compilers. Now, think about this. Let's just say I were to give you, as a developer, some sort of C code. So, of course, I would be writing a .c file. Or if I were writing C++ code, this depends on your convention, but you would usually call it a CPP or a CXX file, right? So, simple. Now think about how exactly your computer, your machine, actually knows what to do with the code that you've written. Now, of course, your CPU is not going to understand C code. It needs to be translated down to machine code, individual instructions that your CPU can go ahead and execute, or at least understand. We'll get more into what exactly the difference is in future episodes. But for now, let's just say we need to take our C and C++ files and we need to convert them to some kind of machine code. So we need to convert from here to, say, x86, or maybe ARM assembly. Maybe we need to convert to PowerPC, right? So it really depends on what architecture you're trying to run the code on. And this is the role of the compiler. Taking your high-level code that's relatively much easier to write and converting it down to machine code. But there's a bit of a problem. When you write code, you have intentions for what you want the computer to achieve. You have some sort of input and you want to get some sort of output. And you're providing the computer with a way to translate that input to output. Now, the compiler needs to understand your underlying intentions behind the code. Because if it can't, then it's going to do a kind of naive translation from your code to machine code, and that is extremely inefficient. Think about it like a loop where you say x is equal to 5, right? And while x is less than 10, go ahead and increment x. So go ahead and take x and increment it by 1. Now, really what you're doing is you're trying to say, all right, we want x to be 9. And if the compiler were to just run this as it is, you would get x is equal to 9 eventually. But it would take a bunch of CPU cycles. So what if the compiler could automatically understand that, hey, you just want x to be 9. So instead of setting it to 5 and then looping through and checking the condition every time and incrementing and doing all of this nonsense, why not just set it to 9? It's that simple. This is called constant folding. It's one of the many optimizations that a compiler can apply to your code to automatically make it faster without you needing to write better code in the first place. It's super convenient. There's all sorts of other optimizations, like, for example, function inlining, where when you call a function, if it's short enough, instead of actually going and calling the function and pushing things to the stack and popping them after, what it's going to do is it's just going to take the code from that function and inline it wherever you called it. It's that simple. And by doing so, it can, in some cases, greatly improve the performance of your programs. But there's a bit of a problem. Almost all of the compilers written in the past were monolithic compilers. What that means is that they would have their own little sets of optimizations or transformations that they apply to your code, and only that compiler would ever be able to use those optimizations. And if you want to introduce new transformations, maybe you want to insert some instrumentation, or maybe you have a brand new idea of how you can make your programs faster for a very specific domain, well, you're kind of out of luck because you have to deal with the monolithic nature of the compiler and somehow integrate your passes, your transformations into it. And this is where LLVM comes in. Instead of having this one black box compiler that takes your code and just blindly translates to machine code, instead, LLVM has a modular architecture, enabling anyone to go ahead and extend it however they wish. So think about it like this. Instead of going directly from C to assembly with a bunch of who knows what in between, what if we could clearly define what exactly that intermediate stage represents for your code? This is called an IR, intermediate representation. More particularly in this case, it's called the LLVM IR, LLVM intermediate representation. So what's going to happen is you're going to take, let's just say, a C file. It's going to go to a .ll file, which is your .LLVM IR file, and this will be converted to your assembly, and of course your machine code. Now, when you convert C to LLVM IR, it's not just static code. The LLVM IR goes through a series of transformations, and then from those transformations, back into LLVM IR code. And this will happen over and over and over again until LLVM says, I'm done optimizing this program. Then an LLVM backend will kick in. And the backend will take this platform generic LLVM code and convert it to platform specific assembly code. For example, let's just say you're compiling on x86, ARM, RISC-V, PowerPC, whatever it might be. No matter what, you're going to have, in most cases, the same LLVM IR code. It'll be optimized the same way, but then depending on the architecture you're compiling for, a different backend will kick in and convert that to native assembly. That is the idea behind LLVM. Now, there are many, many more things you can do with LLVM. For example, let's take a look at some other languages. Now, we know that Clang, for a fact, uses LLVM. Clang is, of course, a C compiler. Now, GCC and other C compilers don't. It's only Clang that uses LLVM. However, there are other languages altogether that use LLVM compiler infrastructure. Some of these most notably would be Swift, Rust, and Julia. Julia you may know as a just-in-time compiled language. So that's right, LLVM doesn't just need to be ahead of time compiled like this, it can even be just-in-time compiled as the Julia compiler does, enabling them to have super powerful in-language features, enabling language or frameworks like Flux and Zygote to even exist. Anyhow, back to LLVM. Now think about this. There's a set of transformations over here inside of this LLVM IR domain. But sometimes, the thing is that it's important to understand the high-level code that the raw C file provides in order to provide more meaningful and language-specific optimizations. Now, if you think about it, C is still relatively low level. And so when you go from C to LLVM IR, sure, you're decomposing structure a little bit, but it's not too bad. However, when it comes to a really high-level language like Swift, where you give up a lot of control to the compiler, you, in most cases, don't manage memory manually. You hand it over to automatic reference counting. Things like this. Because of that, the LLVM code is a lot more lengthy. It contains a lot more instructions to do almost the same thing that you would in C. So when you go from Swift to LLVM IR to eventually your assembly, if the architecture looked like this, you would be losing a lot of architectural information about the program between these two stages. Therefore, the Swift compiler team thought that, hey, instead of going directly to LLVM IR, which is kind of like assembly with types, kind of like in between C and assembly, what if we had two intermediate representations? What if we went from Swift to a different language altogether? What if we went from Swift to this new thing called SIL? And then from SIL to LLVM, S-I-L, meaning Swift Intermediate Language. Then, when we go from Swift Intermediate Language to IR, and then IR to assembly. Each individual stage introduces its own optimization passes, enabling your program to run faster. And here's the thing, because this is slightly higher level, it can understand higher level details about your program, enabling it to do higher level optimizations that enable better and more canonicalized LLVM IR, which can then be further optimized by the LLVM compiler and its transformations, finally converted to assembly code. And here's the interesting thing, the same optimizations that were written for C are now instantly applicable to Swift. The Swift compiler team didn't need to rewrite years worth of optimization and transformations that was already done by the LLVM compiler team. This is why LLVM is so important, being able to reuse code across compilers, across languages, enabling people to get things done faster, enabling all languages to benefit from just a single compiler. That's the idea behind LLVM, and there are so many more things the great teams at LLVM are working on. Now, the primary maintainer of the LLVM compiler and the Clang compiler, actually, as it's the only C compiler supporting Objective-C, has been Apple, of course. But now, Google is contributing a lot to the project as well. You may have heard of the new Swift for TensorFlow framework, which is extensively powered by LLVM features. Of course, because Chris Lattner, the creator of both LLVM and the Swift language, left Apple to join the Google team for their accelerators, and now, of course, leading the Swift for TensorFlow team. And they are also contributing something else, something called MLIR, which will further increase the amount of reuse we can have across compilers, even to things like, for example, Google's TPUs and other accelerators. But that's a topic for an entirely separate video. This, however, is what we're going to be getting into today. We're going to take a look at a few different languages like Swift, Julia, and C, to be specific. We're going to take a look at how exactly these individual intermediate representations work, what they mean, and how they're optimized. And in a future video, you're going to be able to see how you can develop your own transformation and optimization passes, and how you can go ahead and do things like insert instrumentation entirely automatically. And now, let's take a look at how these compilers, Clang, Swift, and Julia, actually use LLVM's compiler infrastructure. Right, so now let's take a look at how you can actually see what's going on behind the scenes inside of the LLVM compiler infrastructure tooling. Now, I will say that while you can use the compiler tools directly, you can actually invoke Clang or Swift C or the Julia compiler with certain arguments to see your LLVM code. Another great way to take a look at LLVM code and even assembly code is through something called the Godbolt Compiler Explorer. It's available at godbolt.org. It's entirely online. They provide you with tons of different compilers, tons of different kinds of compilers in different languages. For example, over here, I can switch over to a C compiler. I can choose which kind of C compiler I want. I can choose a GCC, I can choose the MSVC compiler, the Microsoft compiler, I can choose the Power compilers, these are the XL compilers, and of course, I can choose Clang compilers. So take a look at this. I can go up to Clang 9, I can even go to trunk, but let's just say we want x86 Clang 9 compilation. Now over here on the left, I type in my C code, which is in this case just int square int num, return num times num. Simple squaring logic. But let's just say I did something a little bit different. Let's just say I did int factorial, and I provided int x, and we said if x is equal to 1, then just return 1, otherwise return x multiplied by factorial x minus 1. Now this is a super simple, classic factorial implementation. Now look at this, on the right we get some assembly code that represents the factorial function. Super simple, just like that. As a matter of fact, if I like, I can even go ahead and include stdio, the header file, and I can actually go ahead and print out the factorial of 5. So, just like that, we're printing out the factorial of 5, we get a main function, as you can see, we're moving the number 5 to a register, we're calling the factorial function, we're moving the results over to other registers, calling printf, and so on and so forth. Classic stuff. But wait, we're using the Clang compiler. So we know that before it goes to assembly, it goes to LLVM intermediate representation. So how do we take a look at that? Well, if we pass the -S flag to Clang, that's just telling it emit assembly. So it's going to emit the same thing as it was before. But there's one more flag you should pass, -emit -LLVM. When you pass this flag, it's going to change entirely, and now what you're going to see is LLVM IR code. Now, this looks a lot less intimidating than the assembly code looked, although I will say that it's still not great. From a sort of first time you take a look at this, it looks intimidating still. So let's go ahead and try and understand a bit of how LLVM works. And the way LLVM works is it's written in something called SSA, Single Static Assignment. Now, I will link to some resources so you can figure out more about SSA and what it does. Essentially, LLVM works on this sort of infinite registers concept. So as you can see here, for example, within the factorial function, we have these many registers. We have register 2, 3, 4, 5, etc., etc. And these are just labels for different registers that we're storing things in, over here and here and here, etc. Now, there are also other labels. For example, %1 is the label for the first parameter passed into the function itself. And over here you can see that we're specifying the type of that is a 32-bit integer. Over here we also happen to define that the function will return a 32-bit integer as well. Within the function, there are a few different things we do. For example, the first thing is we have two separate registers where we're going to store the pointer to an allocation of a 32-bit integer. So we're allocating two different 32-bit integers in memory and storing their pointer addresses inside of those registers. Then we're actually storing, let's see, what are we storing here? We're storing the argument that came into the function inside of this third register over here. Now, I will say one thing. A few of these instructions are absolutely useless. This is not the best this code can be. But why is that, you may ask? Well, it's because what Clang did is it did a blind translation from the C code you gave it right to some LLVM code. The most obvious translation possible that works, but isn't fast. It's doing a lot of unnecessary operations. So how can we reduce that? It has an entire register here that it doesn't even use. And here's how you can do it. We gotta tell LLVM, or Clang more specifically, to actually optimize the code. To do this, we're gonna pass it the -O flag. Now, there are a few different levels of optimization. There's -O0, which is don't even think about optimizing whatsoever. Then there's O1, O2, 3, and then there's fast. Fast means enable some experimental, potentially unsafe operations, like for example, working with less accurate floating point division and things like this. I usually use O-fast because the particular applications that I develop don't need the extra safety. But in most circumstances, sort of production level applications are going to use O3 because it's the safer option. In this case though, what's the worst that could happen? Let's use O-fast. So I'm going to go -O-fast in my compiler options here. And would you look at that? Wow, we went from a little bit of LLVM code to a lot of LLVM code. Now, why is this, you may ask? Well, there's one thing I want you to think about. Let's just say we remove O-fast. And let's take a look at our code. As you can see, it's a blind translation. Therefore, on line 21, we're calling the factorial function. I mean, obviously it's a recursive function, so we'd be calling the function again. It's recursive. But if I add the optimization flag back, watch this. If I try and search for factorial, I only get one result. The factorial function isn't calling itself. Guess what happened? LLVM removed the recursiveness from the function. It understood what the function was trying to accomplish and made it a non-recursive implementation of the same function. Isn't that fascinating? Now, because it sort of canonicalized, standardized the implementation of that function, it was able to do another really interesting thing. Now, look at this. Inside of our C code, there are 3 times factorial is mentioned. Once for its definition, once to call itself recursively, and another time to actually call it from the main function. But watch this. There's only one reference to it in the LLVM code. Is the main function not calling the factorial function? Well, actually it isn't. So the constant folding I was telling you about just a moment ago, what happens is this. LLVM actually runs your variables, or your constants in this case, your literal values, through the function at compile time. And it's like, hey, factorial is such a simple function, I might as well just hard code the result for you. Take a look at this. On line 111, in the main function, we're calling the printf function. But the printf function doesn't call, we're not calling factorial to figure out what to print. LLVM has hard-coded the result of factorial 5 into the program for you. LLVM is not looking at the name of the function or what it is. Rather, it's looking at the functionality. It's doing constant folding to say, hey, you know what? We don't need to do all this calculation at runtime. We might as well just print out 120 because that's what they want us to do. What's that? That's what the programmer wants us to do. And that's LLVM sort of thought process there. Iteratively going through these different optimization passes, it enables you to create faster code. First of all, it's removing that recursiveness. It's making it iterative. On top of that, it's making it a better implementation. You see, the factorial function when optimized becomes a lot longer, but at the same time it's faster because each individual instruction is a lot faster, and fewer instructions end up being executed, fewer clock cycles are taken. On top of that, what happens is it inlines the function. So it puts the factorial implementation inside of main, and then it does constant folding and it says, inside of the main function we have all this unnecessary computation that I can do now that I don't need to do at runtime. Let's just finish this now. And that is why these compilers are so great. That's why these are necessary tools, is because they enable you to write such good code. As a matter of fact, in the vast majority of circumstances, writing assembly code manually it actually ends up giving you slower code than writing in a higher level language, because then you have all these compiler optimizations that are making your code faster for you. So that is a quick look at LLVM for C. But there's still 2 more languages to cover, so let's take a look at them. Now, first of all, I'm going to take a look at just using the actual Clang compiler locally to output this LLVM code. It's going to be super simple. So let's just say we do test.c again. This time we'll do the square example. So we'll do number times number, and we're just going to print out the result of 100 squared. All right, now just because we want to avoid a warning, we're going to include this header file as well. So we're just printing out the square of 100. Now, if I go ahead and do clang test.c, then it'll output a binary that I can run, and it'll print out the square of 100. But what I can also do is pass it the -s flag, which will create a test.s file, which is the assembly code for the code that I just wrote. If I also pass it emit LLVM, then it'll output a test.ll file, which is the LLVM code. So now here's what I'm going to do. I'm going to remove the binary and the S file, and now we've only got the LLVM code. So I'm going to say cexample.ll or mvtest.ll, cexample.ll, and there we go. So we've got test.c and cexample.ll, which is the LLVM code for that C code. But now, let's take a look at some Swift code, shall we? So let's just go ahead and type vim test.swift. So we're going to create a super simple Swift file. We're going to create a function called square. It takes number, which is an integer, returns another integer, which is just number times number. And it prints out square of 100. All right? Now, if I run swift test.swift, it prints out 10,000, just like Clang did. But I can do swift c test.swift, and I can tell it to emit IR, which will emit the LLVM IR code. Now, yeah, so I can tell it to emit IR, and I can tell it to output to swift example.ll. Now watch this. If I open up this file, get ready to see quite a bit of code. There we are. So much code. Now, if you take a look at what's actually happening here, as I mentioned, Swift is a much higher level language than C is. And therefore, there are many more operations that go behind doing essentially the same thing in Swift. Now, when this gets compiled down to assembly, likely a lot of this stuff is going to go away. But in this case, it isn't. This is raw LLVM IR from the Swift compiler. Remember, both Clang and Swift that we've taken a look at so far have not introduced any optimization passes. We'll take a look at what it looks like then in just a moment. But as you can see, this is all of the LLVM IR code that Swift generates. That is a lot of IR code, at least relatively. All right, but now let's take a look at Julia. Now, remember that Julia is a just-in-time compiled language. So we can't just call it and say, emit the IR for this entire file, because it does it function by function, not file by file. So let's go ahead and actually run the Julia repo and go ahead and interact with it a little bit. But first, a quick primer on the Julia language. The star operator is a bit special in this language. So for example, you can do 5 times 5, and of course you would get 25. You could do 25.6 times 23.12, and of course you would get whatever the result of that is. But the star operator in Julia is also the string concatenation operator. So for example, hello times world would result in hello world. Now let's just say we were to create a function called f, and it takes a variable or parameter argument called x, and it returns x times x, end. Now Julia is a compiled language, but we didn't tell it what the type of x is. So how in the world does it know what to do with x? Well, watch this. This is almost like a magic trick. I can pass it the number 5. Guess what it returns? 25. I can pass it hello, and guess what it returns? Hello, hello. I can pass it 5.67, and it returns 5.67 squared. Isn't that absolutely exceptional? But what's super interesting is that we can take a look at the LLVM code for all these different compiled versions of the f function by using a little macro called @code_LLVM. I type that out and I tell it what I'm going to invoke. For example, let's just say I'm passing an integer to f. Then as you can see, it creates LLVM IR code, assuming we're taking an integer 64 and returning an integer 64, and returning it multiplied by itself. Super simple stuff. So then, how about we do floats? So let's just say I were to pass 5.67. Now, as you can see, it's looking for doubles, and it's doing a floating point multiplication. But what if I pass it a string? Look at this. When I pass it 10 just like that, so much more code to deal with the string involved. So every time you pass different arguments, Julia's actually going through and saying, does this function make sense if x is a string or integer or double? If it does, go ahead and compile it to LLVM and then provide the user with the result of the execution. And what's interesting is, every single time you actually run a function, the first time it'll compile the LLVM code and optimize it, and the second time, and so on and so forth, it'll use the cached version of that function so it doesn't keep compiling, or else, of course, there would be no point to using the language because it would be too slow. You're recompiling the function every single time you call it. And so that is how Julia uses LLVM. And so that is how Clang, Swift, and Julia use LLVM in their own ways. One more thing I want you to take a look at though. As you can tell, we have LLVM IR files for 2 different languages, Swift and C. Both of them were created assuming no compiler optimizations in mind. But let's redo that, this time assuming we do want compiler optimizations. So I'm going to do clang test.c. This time I'm going to pass ofast to make it optimize as much as it can. Then we're going to do semit LLVM, and we're going to output to cexample.ll. And we're going to do something similar for Swift. Now, Swift doesn't have levels of optimizations. Either you are or you aren't optimizing, or you're optimizing for binary size instead of speed, which I rarely ever do. And so in this case, we're just going to pass it -o because that means optimize for speed. From there, I'm going to tell it to emit IR, and we're going to output to swiftexample.ll. Now let's take a look at this C version of the LLVM IR. How simple is that? The square function is literally just multiply the argument against itself in return, and the main function, well, it's not even calling the square function. It's just printing out the hard-coded result of square, and, of course, that is 10,000 because we're looking for the square of 100. Now, what's interesting is that while the Swift IR is still a lot longer, it is doing fundamentally the same thing. Take a look at this line of code. It's storing this hard-coded 10,000 inside of a variable, which it then passes over to print, and it gets printed out onto the screen. So it's actually pretty simple. If you take a look, Swift and C both did constant folding thanks to the same optimization passes. That is absolutely exceptional stuff. Code reuse is always good, and the fact that LLVM is open source, being maintained by large companies like Google and Apple, and has so many developers working towards it, you can be sure that your code is being optimized as thoroughly as possible, and people are working towards more and more. Even companies like IBM are contributing towards different optimization passes. For example, loop optimization passes, loop merging, all sorts of things. One more thing I want to leave you with before I go. As I mentioned, Swift doesn't just compile to IR. It compiles through another intermediate language called SIL, Swift Intermediate Language. So let's take a look at some of that, shall we? Now, we can compile in a very similar way, except this time we're going to emit SIL instead of emitting IR, and we're going to save it to a different file. So I'm going to open this up, and there we go. We got SIL. This looks kind of like if you were to take Swift and LLVM and kind of go in between but a little bit closer to the LLVM side, whereas LLVM looks as if you went between C and assembly sort of right in the middle, right? So you're going from Swift to something a little bit closer to Swift, not quite at LLVM, and then you're going to LLVM, and then you're going to assembly. And by doing this, at every stage, you can introduce further, lower level optimizations that you could never achieve with a simple monolithic architecture. That's the power of the Swift and generally LLVM compilers. Taking a look at this is all SIL code. Now, because this has optimizations, there's a chance that the hard coding and the constant folding occurred over here. Let's take a look. Indeed, it has. As you can see, the constant folding that was necessary for Swift to say, you know what, instead of calling square, we'll just print out 10,000, that actually happened at the SIL phase. So it didn't even make it to LLVM. And this enables LLVM to apply its optimization passes better. Now, just so you're aware, another thing that LLVM does is called canonicalization. This does things like, for example, let's actually take a look at a simple file here. If I were to do something like int fx, and this just returns x plus 1, or we could say if x is not equal to 5, return 1, otherwise return 0. Well, in this case, what's happening is if you were to take a look at the canonicalized, or fixing the C syntax here, if you were to take a look at the canonicalized LLVM for this, instead of saying if x is not equal to 5, then return 1, otherwise return 0, it'll flip that around, and it'll say if x is equal to 5, return 0, otherwise, or if it's, so it'll basically switch the true and false from the else above to the regular if. Or, for example, if it's doing x minus 1, instead it'll do x plus equals or plus -1. By doing this, it standardizes the format for certain operations and enables optimization passes to look at only certain kinds of operations instead of having to look at a wide range of different operations. And so by doing that, it enables optimization passes to have an easier job. And so that is how LLVM compiler tooling works. Now, in the next few videos on LLVM, we're going to be taking a look at how you can actually use the LLVM Pass Manager to introduce your own instrumentation into different functions. And from there, we're going to be taking a look at brand new stuff in the world of LLVM, hopefully things like MLIR, very, very soon. But that's all we have for this tutorial today. I really do hope you enjoyed. If you have any questions, feel free to leave them down in the comment section below, email them to me, or tweet them to me at Tajimani. Apart from that, if you do enjoy the content on this channel and you want to see more of it, please do feel free to subscribe. You'll be notified whenever I release a new video. Once again, thank you very much for joining in today. Goodbye.